Hi again, this is now Biomechanics Module 2, where we will do a short introduction to kinetics. Remember, kinetics now deals with the forces on an object, and we define that basically as a push or a pull. So force has to be applied in either of those two mechanisms. We represent forces with an arrow. More technically, it's called a vector. And that vector has four important attributes that we need to be considering. The first is magnitude. So how much force is being applied, either through a push or a pull. When we represent a force by a vector or an arrow, the length of that arrow indicates the magnitude of the force. So typically the longer the arrow, the greater the force. The direction is pretty self-explanatory. That's in this case, the direction is to the right, but we can describe that in anatomical terms as we get started looking at the effects of forces on the body. The third one is the point of application, and as we apply a force, the point of application is the non-arrow end. So we're thinking about this point, and we want to apply that end of the vector to the point of application of interest. Typically that's going to be the center of mass, but if we're starting to draw a diagram of, say, how weights might affect somebody's motion, or how our hands are applying force to a model or a system, that point of application could be applied somewhere else. And then the last attribute is the sense, and that has to do with an XY coordinate system, and we're not going to deal with that much here, but you may see that again in biomechanics starting in the winter. The amount of force is a Newton. That's how we quantify forces. And a Newton is described as the amount of force needed to accelerate a 1 kilogram mass 1 meter per second squared. So acceleration, how much force does it take to get an object moving or change its uniform motion, right? If you apply a Newton, you're going to apply enough force to move that mass 1 meter per second squared, or accelerate that mass 1 meter per second squared. So there's some equations that we use to kind of get our head around how forces are applied, and there are some. This is pretty basic description of what forces produce, right? If you think about it, if you push or pull on something, that object will move. If its mass isn't too much, you'll move that object in a line, right? In the same direction that the force is applied. So our prior force vector was to the right. If we were to push on an object using that vector, we would push it to the right. That's a translation. We could also produce a rotation. If we apply that force at a point that's not directly through its center of mass, that would create some spin. Or if that object has an axis of rotation, which would constrain its ability to translate, but would allow it to rotate. So we can also get angular motion or rotation when we apply a force. I'm going to back up to the linear equation that is often used. There might be some others, but sort of the basic one is a force is equal to mass times acceleration, and we can manipulate those variables a little bit to, for example, understand how much force is applied if we know the mass of an object and we can quantify its acceleration using motion capture, for example. So that's a pretty straightforward equation that gets used quite regularly in applications of motion analysis. For angular motion or rotations, here's one equivalent equation. So torque is sort of equivalent to force in the translation description. The mass moment of inertia is somewhat equivalent to mass, and then angular acceleration is equivalent to acceleration. So I like to think about this as this idea of mass moment of inertia. If you can see the two people on the swing sets there, one of them won't require much force at all to get swinging, and that would be angular motion, right? The other one's going to require more force to get moving, the bigger guy on the left, right? Because they have more inertia in their system. A larger mass means more inertia, more difficult to get angular rotation started. So that's kind of how that equation applies. Of course, a linear motion and an angular motion can happen together at the same time. So you might see this curvilinear motion. There's both translation and angular rotation taking place. And then another really important thing that we think about as clinicians is tissue change. Any force that's applied to the body, and we're almost always experiencing a force, results in changes to the system. And we're going to get into the specific details of that on the next slide. But stress is a change in the force per unit area of a structure. And when we apply a stress, we typically have some type of strain, which is a deformation or a change in the shape relative to the original shape. So here's that concept in a little more detail with a couple of graphics that hopefully will be helpful. If we apply a force, a push or a pull, we're going to do something to a tissue or an object if it's deformable. And in the body, most of our tissues all of our tissues are deformable. Even bone has a little bit of deformation each time we apply a load to it. So push or pull on a tissue, it changes the force per unit area, and that results in a deformation. So if we think about this, I like to think about these things like little cigarette butts. I don't know, maybe little pool noodles would be a more health conscious description. But if we think about this unloaded tissue here or object, it's sitting right about here. It doesn't have any stress on it. There's no force applied to it. And so it isn't deforming, right? Nothing's happening to it. But if we apply some tension to it by pulling on it and increasing the stress in one direction, a linear direction, now that tissue is going to deform and it's going to start moving along this strain axis as well. So as we apply stress, we get a change in strain, and it's going to head up this curve like so. As long as that tissue stays in this region, it's going to manage that stress with no problem, and as soon as that stress is taken off, the tissue will go back to its normal unloaded shape. The problem comes in this area. That's the first sign of trouble comes in that area, where that's the plastic region, and that starts to make some permanent changes in the integrity of the tissue, such that once that stress is released, the tissue doesn't necessarily go back to its original shape. It might stay a little bit elongated in the example of tensions, right? If you keep applying tension, and work it into that plastic region, you might have some permanent deformation. And then, of course, you reach a point where that tissue will fail and it'll be disrupted. So many of you have had ACL injuries or know people who have had ACL injuries or have been in the clinic watching rehab of people with ACL injuries. That's what's happened. That ACL, anterior cruciate ligament, has been stressed and has elongated in a way that overcame its integrity and it ruptured. So you can apply compressive loads to a tissue. You can apply a bending load. There are shear forces where you have oppositely directed forces, these little arrows. Torsion is a twist, and then these types of loads can happen in all sorts of combinations. Here it's compression and torsion happening at the same time. So this is a really important concept when we think about injury mechanisms and just how tissue is loaded and unloaded consistently and regularly in the human body. So what are those main forces that we are dealing with or think about in our clinical application? Well, we can split them into internal and external forces. Internally, most of the forces we're thinking about are generated by muscle, so muscle contraction. And a muscle can't push, it can only pull. So you can't push a rope, right? So a muscle contraction is always a pull between its origin and its insertion. There are some other forces that can be applied and are applied, and some of these are used to prevent motion at our joint level, restrain motion. Our ligaments restrain motion, so they're going under tension and they're limiting motion, for example. Well, those are forces internally. So there's a whole list of them there. I put muscle again because muscle also has a non-contractile element to it. If we stretch a muscle passively, it starts to load, it starts to gain tension, and stress increases, deformation starts to increase. So I put that in the list as well, but you can see there's a long list of internal and even external with skin that can provide forces on the body. So muscle's the main one, and then when we go to the external forces, really gravity and the ground are the two main external forces that we concern ourselves with as physical therapists. Gravity is a constant force, always acting on the body, and then as we hit the ground, there's a ground reaction force, an equal and opposite force that is applied to our body from the ground. The same principle applies to other stationary objects. If you push on a wall, you get a reaction force. If you sit on a chair, you get a reaction force, etc. So we sort of use ground as a kind of a universal term to represent those other reactionary forces that you'll also have. Of course, if you're holding something, a grocery bag or a dumbbell or a suitcase, those are also applying loads, and they're an external object. Wind and air provide some external forces. Water, friction's a really important force when you think about things like walking and running and stopping. And then also really important for our application as therapists, our hands are really important for providing forces. We use braces to augment the internal system that may not be able to provide the right restraints to motion, so we might put some braces on. And then we use assistive devices and other equipment that will also provide forces. So there's a lot of forces to think about, both internally and externally. Another concept that is important is center of mass, and it's important to understand this in terms of setting up our problems for analyzing motion. So every object, whether it's a piece of styrofoam or a bowling ball or your car or the human body, composed of a bunch of different types of matter, right? Sometimes that matter is uniform, as in a bowling ball. Other times that matter is different, and it has different mass. So bone has different mass than muscle, that has different mass than cartilage, that has different mass than the brain, right? So, but together you get this composite mass to a system. The center of mass is the one point at which all that mass is equally distributed or balanced. And so if you can imagine, if you look at this object right here, it's sort of a blob, but it's got this little thing sticking out. It's got this little extra bump on it. It's not perfectly round, right? Well, that, if you think about it, you have to sort of take a weighted, W-E-I-G-H-T-E-D, a weighted average to that mass to figure out the center of mass. So for example, you could look at a set of 3 second-year students and imagine where the center of mass is in their heads.
Hello!
Hi!
Thanks.
Bye, Dr. Morstead. Bye, Dr. Morstead.
See ya. All right, they made me do that. Finally, then, this is really important because we sort of use that center of mass, that hypothetical point, when we're considering the effect of forces on an object. So I think I mentioned earlier that if you put a force directed directly through that center of mass, you'll create a linear motion, and if it's off-center, you'll create some angular or a curvilinear or combined motion. One of the things about the center of mass is that it can change based on how the body is positioned. On the left here, we have somebody that's basically in anatomical position. Their hands aren't perfectly in anatomical position, but the center of mass in the typical body is at about the level of the second sacral vertebrae, so S2, sort of in the middle of the pelvis. Okay, so if you, in theory, if you could, put that point on a stick, the body would be balanced all the way around that point. In this pose now, the person has raised some of the mass of their leg superiorly. They have raised their arms overhead, and so they've redistributed the mass of their body more vertically. And so the center of mass would be now above S2. It might be more at like L4, okay? Because the distribution of mass has changed a little bit. And then in this final pose, the person has distributed their mass much more to one side of their body, and so that instead of being right in the center of the pelvis, it's now shifted laterally in the pelvis, and it's more it's located more to one side of their body. So the center of mass can adjust based on how the mass is distributed. Likewise, if we look at this picture, this person is doing a bilateral shoulder abduction. They're up at 90 degrees. If we were just to look at their arms and consider that mass, we'd say, okay, the upper arm has more mass to it than the lower arm, than the forearm, so we might put that mass about here. But there's also a hand attached, so that adds a little bit of mass. So now I might move that center of mass closer to the elbow. But further, she's now holding a dumbbell. I don't know what that weighs. Looks like it's maybe 5 pounds. But that also moves mass distally. And so we probably want to consider or think about that hypothetical center of mass like in the upper forearm, right? We would draw a vector off of that center of mass, the application. That is the vector that represents gravity acting on the arm that is holding a weight. So that's why we want to conceptualize where the center of mass would be, because it helps us to consider now what are the muscle requirements to create this motion, and we know it's the deltoid, and we know then the deltoid pulls in that direction to abduct the arm. And so these are two competing forces. We could also think about, I'm going to draw these in, I'll draw these in orange. We could also think about the compressive forces that are happening at the glenohumeral joint, where the humerus is being pulled into the glenoid by the muscle force. So there's a whole lot of different forces we can consider here in any given scenario when we're looking at human movement. So for your homework, which we won't hand in, but you should do this as an exercise, look at these two motions. They're snapshots in time of two exercises, and you could draw the force vector that represents gravity, and you could draw the force vector that represents the main muscle that's performing the motion. This is similar to the picture we just saw. She's just elevating her arms in a different plane, and this, of course, is a sit-up exercise where the abdominals, the rectus abdominis, is the main muscle that's active. So that is Module 2.